Our last lecture would be about Cauchy's integral formula. This is a very important formula in complex analysis. It can be derived from Cauchy's integral theorem. It is very useful in evaluating integrals, as we will see in this section. Also, it has many other important uses, such as proving that analytic functions have derivatives of all orders. So you can differentiate an analytic function indefinitely. Also, it's very useful in showing that all analytic functions have Taylor series representation. Okay, the formula says if f of z is an analytic function in a simply connected domain D, then for any point z0, any complex number z0 in the domain D, and any simple closed path C in D that encloses Z. So you have a domain. In that domain, you have a simple closed path C, and that path encloses the point Z0. Then the integral of this function, okay, so it's not the integral of f of z, but the integral of this function, which is the ratio of f of z divided by z minus z0, is equal to pi I times the value of the function f at the point z0. In applying this formula, we use a very simple fact that we learn in Math 095. Okay, if you have A over B, C, A, B, and C could be anything. Mostly B would be something like this, Z minus Z0. Then this is equal A over C over Z minus Z0. The idea is that we want to isolate Z minus Z0 so that we can apply the formula. In this case, f of z would be this. Okay, example. Let's say you want to find the integral along the closed contour. If along any closed contour, okay, so doesn't matter what closed contour we are integrated along, only one fact matters. That closed contour, does it include the point 2? In this case, the point 2 is z0, or it does not. Does it include the point 2 or not? If it does, okay, since f of z is entire, it's analytic everywhere, so it satisfies this condition. If it does, then we can apply the theorem, and in that case it's 2 pi I f evaluated at z0, which in this case is 2. F evaluated at 2. F is e to the z. So it's 2 pi I e to the power 2. Since the input of e is a real number, the exponential function, the complex exponential function, reduces to the real exponential function if its argument is real. So this is simply 2 pi I times e squared. E is 3.7 blah blah blah. Okay, and in that case you get that number. If, on the other hand, we are considering closed contours that do not, such as C2, that do not include or enclose the point 2, then, as we know from Cauchy's integral theorem, the integral is 0. Okay, because this can be using the theorem, as you recall, this contour can be reduced to the point 0. All right. So here it doesn't matter which contour we have. Okay, there is only one property about this contour that is important. Does that closed contour include 2 or not? If it does, then Cauchy's integral formula applies, and this is the value of the integral. If it does not, then the value of the integral is 0. Okay. Example 2. This is the function we need to integrate. We have to figure out what is f. Remember, we have to reduce it into something that looks like this: z minus z0. Okay, our integrand should be reduced to something like this. What we have in the denominator is not z minus I, we have 2z minus I. So we have to get rid of the 2. Okay, so this is z cubed minus 6, and this is, take the 2 common, so this is 2z minus I over 2. Now to get rid of the 2, you have to divide by 2. So divide here by 2, but then you also have to divide the numerator by 2. Otherwise, you would be changing the function you are integrating. So z cubed over 2, 6 over 2 is 3. That's the numerator. And the denominator, the 2 cancels the 2, and you have z minus I over 2. So in this case, z0 equals I over 2. Okay, so this is z0 is I over 2, and f of z, okay, because remember we need f to evaluate the integral, and f of z is this part. F of z is z cubed over 2 minus 3. All right, if you do that, then you simply have to evaluate f of z at z equal I over 2. If you do that, you have, so this is basically 2 pi I, z equal I over 2, so you have 1 over 2 I over 2 cubed I over 2 cubed minus 3. So this is 2 pi I cubed is minus I, and 2 cubed is 8 times 2 is 16 minus 3. Now if you multiply this out, I times I is minus 1, and we have a minus, so this is equal to 2 divided 16 divided by 2 cancels the 2 factor from 16, so that's pi over 8. 2 pi times minus 3, 2 pi I times minus 3 is minus 6 pi I. And this is the case, okay, because in this example, I over 2 is inside the closed path, closed contour C. So basically here we don't know anything about the closed contour, and we don't need to know anything about the closed contour except this. Otherwise, if we are told that this is outside C, then simply the integral would be 0. Okay. So the trick here in this example, again, to figure out what is the function f of z. This is the closed contour we are interested in, closed contour C. And we're told from the picture that it includes the point 2. This is important. Why? Because z squared minus 4 equals z minus 2 and z plus 2. So the function is not analytic. Okay, not analytic at z equal 2 and z equal minus 2. So what we need to do is the following. We write our function cosine z over z minus 2, z plus 2. Okay, we want to write it in this form, f of z over z minus 2. Okay, we want, since 2 is inside, okay, we want z 0 to be 2. Okay, since 2 is inside, enclosed by the contour C, we need 2 to be z2. So this is gonna be equal cosine z divided by z plus 2 over z minus 2. So now this is our function f of z. And the integral becomes integral cosine z over z squared minus 4 closed contour dz equal integral closed contour over z minus 2 cosine z over z plus 2 dz, and this is equal to pi I f of 2. Okay, so 2 pi I cosine 2 over 2 plus 2. Okay, 2 plus 2 is 4, 4 divided by 2 is 2, so we have pi I over 2. This is cosine 2, not cosine squared. Cosine 2. Whatever cosine 2 is.